Woo. All right, cool. Nice. All right, yeah, so my name's Christian Gilbertson. I'm a first-year grad student here at Penn State, and I'm here to talk to you about space debris. And I'm also really proud of this title slide, so... yeah. All right, moving onwards. So, brief overview. I'm going to talk about orbits, what they're shaped like, what space debris actually is, and kind of what the problems it causes, and then maybe how we can deal with it. So, orbits. There was a German dude named Kepler in the 17th century who wrote down some general rules for how orbits of the planets work. So, they're in the shape of ellipses, and they go faster as they get closer to the sun. And planets that are further away from the sun take longer to orbit than planets that are closer. Although I'm not talking about planets in this talk, I'm talking about satellites, but there's a good comparison to be made where if that's the sun and this is a tiny little Earth, you might be able to draw a similar picture with Earth and a tiny little satellite. So he might as well have written these laws as the laws of satellite motion as well, but they didn't really have those in the 17th century, so that's more of a now thing. Yeah, so to give you an idea of some numbers, so for things that are 400 to 500 kilometers from the surface, like the International Space Station in Hubble, they're moving like 7.5 to 7 kilometers a second. Things further away, and these take like 90 minutes to orbit, roughly. And then things further away, like GPS, which is 20,000 kilometers from the surface, and geostationary Earth orbit, which just means that it rotates with the Earth. Its period is 24 hours. Those go a lot slower, like 3 to 4 kilometers a second. So, what's space debris? Space debris is basically things in space that we're not really using anymore that we put there. So some examples are old satellites that have finished their missions, old rocket upper stages, remnants from putting up satellites or other missions, and also smaller fragments, things like pieces of paint, unused fuel, and some like explosion remnants. So basically it's space garbage, just kind of floating around there. So why should we care about all this stuff? Like, space is pretty big, like, it's basically an awesome dumping ground, one might think. But things floating around in space can cause a lot of problems. For example, you have to worry about these pieces that are floating around hitting missions that you want to keep going, things that you actually want. So that's a problem. You have to worry about the increased cost of missions when you have to worry about protecting your spacecraft, and you also have to think about how just having space debris up there makes planning your mission and the actual operations more complicated. So this is like what happens, for example, if one tiny piece of paint, like a paint fleck, hits the window of the space shuttle. Yeah. So another thing, like kind of a doomsday scenario, why we would care in the long term, is there's this thing called Kessler syndrome, where if you have, a lot of our satellites in what's called low Earth orbit, so like pretty nearby, and say two of these satellites hit each other and blow up, then there's a lot more debris. You have a lot of tiny fragments going around, and what if those fragments hit something else, and all of a sudden low Earth orbit is just now this disgusting cluster F of little pieces just going around, basically making low Earth orbit useless. So that's like kind of a really bad thing that could happen. So, and it might make going through low Earth orbit something like navigating a asteroid field where you don't want to know the odds of getting through it. All right, so there's two different regimes that you kind of have to worry about. So low Earth orbit, I've mentioned, and it's this one that's really, really close to the Earth. And one thing that's good is that there's still a decent amount of atmosphere there, so orbits that are just chilling will decay over time. Like, they'll actually kind of slow down, enter the Earth's atmosphere, and eventually burn up on their own. But there are a lot of downsides, so the periods are a lot smaller, basically how often it's going around the Earth, and the speeds are a lot higher. and there's a lot more stuff there. Like, it's really valuable real estate, and there's really not that much of it. And so since their orbits can be oriented very differently, you kind of have to worry about collisions coming in from all different directions. And this is kind of the regime where Kessler syndrome that I mentioned earlier is more prevalent. And then there's basically everything else. And for higher altitudes, there's a lot more space. Things are going a lot slower, and they're moving by a lot less often. So you don't have to worry about things as much. But there are some downsides where, like, geostationary Earth orbit, when you're moving, when you're rotating kind of, or revolving like with the Earth's rotation, that's like really valuable. So if you do mess that up, that would really suck. So you have these shared orbital paths, and there's also very little air. So orbits that are really far away from the Earth will last a really long time. They won't just kind of decay on their own. So where are we at right now? Well, the way we find space debris is you can either use radar or optical. So radar measurements are better close by because you have to project the power that's reflecting off the space debris. So you have to project it, and then it reflects back, and so you kind of lose power going both ways. But you use optical measurements to see things kind of further away because you're just getting losses one direction because you're using photons from the sun. So NASA and the Department of Defense both have an interest in measuring this debris, and it's cataloged in the United States Space Surveillance Network. And this is just a picture of the Haystack Observatory at MIT, where a lot of radar measurements of space debris are taken. So just to throw some numbers out there, I didn't check these with the numbers they had on the kind of like slide going before my talk, but this is what I found. So less than a centimeter, you have like 170 million pieces of debris. A little bit bigger, around 700,000, and a little bigger than that, around 30,000. And a decade ago, it was estimated that there was almost 6,000 tons of debris just nearby in low Earth orbit. And this is a cool plot that I'm actually going to blow up. And it basically shows the trend of how much space debris has kind of been accumulating over time. And it starts in the 60s, as you might expect, and kind of goes up pretty linearly. And there's some big steps that I'll actually kind of mention where they come from later. These are from like individual incidents that have really big impacts on the total amount of space debris. So you kind of see maybe if a couple of these happen, it makes it more likely for these to happen, and it could just skyrocket and be a mess. So not to freak you out, but accidents have already happened. So in 2009, a U.S. Iridium and Russian Cosmos satellite collided at what's called hypervelocity, which is greater than 3 kilometers a second. So you can maybe imagine two satellites just kind of slamming into each other that fast can kind of create a mess. Both satellites were completely destroyed. They created about 1,000 pieces of debris, like big debris, all on their own. And the International Space Station actually had to maneuver to get away from the debris caused by this wreckage. So I also, on Wikipedia, found some really cool images of like what happened after this collision. So they collide over Siberia. 20 minutes later, they're just kind of two of their own little cloud of debris. And then about 50 minutes, so about halfway through, I said the International Space Station was like 90 minutes. So these are also close by. So like halfway through their new orbits, they've kind of recollimated, but now they're just pieces of debris kind of sitting in their new orbits. And that is this bit. So that's in 2009, this smaller jump. Next big thing, in 2013, some debris from a Chinese anti-satellite missile test hits a Russian nanosatellite. So this is the Fungyun satellite that China blew up in 2007, and that was the biggest space debris generating event ever. And it basically screwed with the orbit and orientation of this Russian nanosatellite. And that missile test is this big bump. Finally, another thing I found in 2013 was this CubeSat interacted with some debris around a old rocket upper stage, and that caused it to spin pretty wildly about its axis, but they eventually recovered it, and it wasn't that bad. But yeah, upper stages can also be a part of the problem. So, also, I feel like I had to add this. In February, we put a car in space, so that's pretty cool. It doesn't really, I don't really categorize it as space debris that much, just because it's so far away. Like, we don't really have to worry about it for nearby missions or anything like that. But some collaborators I work with in Toronto also have said in the next 3 million years, there's a non-negligible chance that it hits either the Venus or Earth, like around 15%. So that's just a fun fact. Yeah. So what can we do about it? So, ironically, a month after China did its anti-satellite missile test, this meeting was already planned, but the UN Office for Outer Space Affairs put out this kind of document with some mitigation guidelines, and they're pretty common sense. Like try not to release stuff during your mission, don't hit anything on accident, don't hit anything on purpose, not pointing fingers, and yeah, and try to like limit long-term presence in the valuable orbits in geostationary and low Earth orbit. So what can you do for your specific mission? Well, to protect yourself, there's this thing called monolithic shielding. And what that means is put a big block of aluminum between you and whatever. They really like the term monolithic. They don't like to say put a literal wall between you and whatever. I guess it's just more technical. It sounds cooler. Like better on a proposal. But you can also do something a little more refined called Whipple shielding, where you put like a sheet of like Kevlar, and hopefully when the debris hits that, it like fragments, and whatever's behind it has a lot more surface area to deal with the energy of the impacting particle. Or the International Space Station semi-regularly has to maneuver around debris that's going to get, I think it's within like 100 meters or something. They like move out of the way. In terms of protecting others, you, at the end of the mission, probably should put your satellite either in a graveyard orbit, which is an orbit that no one plans to use, or just, kind of deal with it by sending your satellite into the atmosphere so it's just kind of totally out of the picture. So there's some methods that have been proposed for active removal. One idea that Japan has is attaching something to a piece of debris and then like unspooling this 700-meter long tether that interacts with the Earth's ionosphere and magnetic field and kind of drags both of them down. Another thing is using solar sails. So this would be more if this would be something you put on your mission before you launch it. And the idea is when you're done with your mission, you kind of unfurl this sail, and either if you're really high up, you can use the momentum from like photons coming from the sun to create some drag and eventually enter back into the atmosphere. Or if you're close to the Earth, you just have a sail that just hits, it's just bigger surface area, and you get more atmosphere and you get more drag that way. So there's a place in England who's kind of working on that. Another idea is to grab big pieces of debris, either with like a harpoon or nets. And the European Space Agency is working on that, as well as that same place in England. Actually, this removed debris experiment is really cool because they're going up and they're basically deploying 2 little CubeSats. They're like generating their own debris and then trying to like grab back onto it with different experiments. Like they have a net and a harpoon. So the last method is a little more out there. So it's using so Japan wants to use a ground-based laser not to like totally incinerate big pieces of debris. This is more of like a mass cleanup thing, where you have these small pieces and you just kind of pulse at them with a laser, and it creates a little puff, and it's just enough to change the orbit and hopefully send it back into the atmosphere. And a Chinese professor just this last month in a magazine or journal called Optics suggested that we do this with a space satellite, and that generated a lot of press. I don't think he's the first one to do it, but that's just a story I read recently. So, some conclusions. Space debris is a problem, and it'll only get worse on its own as we put more and more stuff into space. But there are ways to fix it, both preemptively and actively. So, I hope you liked it.
Do you have any sense of how long it would take using a solar shield to slow something down?
Okay, yeah. So, do I have any sense of how long it would take for a solar shield to or a solar sail to deorbit a satellite? And the answer is no. To put it realistically, I don't have an exact idea of the numbers for that.
Could we just kind of slingshot it over to the sun and just let it all get incinerated? And also, could we do that stuff with say nuclear waste? Just send stuff to the sun and let it disintegrate? Or?
So my intuition is that would be. Oh yeah, sorry. So the question was, can we just send this debris along with maybe other waste products like nuclear waste into the sun? Would that be easier? My intuition is no. I think it's a lot easier to just change their orbit slightly, and because all you're doing is imparting a little bit of energy and just redirecting them into the Earth's atmosphere. To get things all the way out to the sun, you'd have to impart a lot more energy to get the debris totally out of the Earth's gravity well, and it would be, basically I think that would just take a lot more, because part of the problem is just grabbing onto the debris. Like that's the biggest issue right now, is selecting what you want, grabbing onto it. But there's a very big consensus as the easiest way is just destroying it by putting it into the atmosphere. Sending things out to the sun would be very, very expensive, like fuel and energy wise.
Could we do that with our toxic waste? I mean, is that feasible? Or?
Presumably. I mean, I think that it's. Oh, sorry. He reiterated asking again if we could do that with toxic or nuclear waste. In theory, yes. I just think it would be incredibly expensive, and if we can't even right now, if we can't even get funding to put up all the space missions we want, I doubt it would be easy to get Congress to get funding to launch hundreds, tons and tons and tons of stuff into the sun.
It's harder to get to the sun than to get to Mars. Just
That-
to give you a perspective,
yes.
much more difficult.
How big does a piece of space debris need to start out That's super impressive.
Okay, so he asked how big does a piece of space debris need to be in order to get all the way through the atmosphere and impact the ground. My guess would be on the order of, this would just be analogous to asking, because most space debris is solid, you don't have a lot of hollow things, so it's basically analogous to how big does a meteor need to be to get through the atmosphere, and I think that's on the order of a couple meters, 10 meters. I might very well be wrong there, but I think it's kind of on that size.
So if you're sending these pulses to nudge these particles so that they can fall back in, do they worry about, if this doesn't work, if it doesn't go back in, now you've just sent it on an entirely new trajectory that could mess things up even more. It's disturbing the cloud. Are you going to disturb the cloud by trying to fall back in?
Yeah. So, presumably sorry. I know. I'm sorry. Okay. So he asked, do we have to worry about, instead using the lasers, do we have to worry about sending things just into, even more problematic orbits instead of ones that perfectly, just go down into the Earth's atmosphere? I think that they're probably going to do smaller, they'll scale up how much debris they're hitting as they get, more precise and more confident that they can actually do what they want. But even then, sending things, they're doing that to mostly debris kind of in low Earth orbit. So if you kicked it into a further out orbit, you might just be kicking it into a graveyard orbit anyways. So I wouldn't really see that as a big issue.
had one question. I'll use the mic. So you mentioned, I think it was Kessler syndrome. Are there any like predictions based on the curve that we had on Earth? How long it would take to get to that spot?
Well, as you might guess, that's heavily dependent on where it starts, because it will have like a typical exponential growth where like once it starts ramping up, like it really goes crazy, and it's pretty sensitive. It's basically sensitive to mitigation, because now like there's more standards in place that that will like decrease the amount of debris we're generating and hopefully level it off. But I think I read like if we did not mitigate at all, I think some estimates put it as within the century that something would happen that would like basically put this on the road to happening.
Any other questions?